call your attention, we will meet again in 2 weeks. I have a terrible feeling I've misspelled the speaker's name. He's from Oxford, but that is the correct spelling of his title. And it's apparently not the obvious stratification of a CW complex.
All right. Okay, so I just want to say a few more general things about canonical forms. First, so there's a variety of ways that you can compute canonical forms, but let me mention one of them that we'll use over and over again. So let's say you have a complicated, or more complicated space, positive geometry, the pentagon in this case. Then, if you break it up into the sum, if you triangulate the space, it doesn't have to be into triangle, but you break it up into regions that geometrically are non-overlapping except along boundaries, and add up to the whole space. In other words, if you triangulate, if T is a triangulation of the positive geometry, then the canonical form for P is the sum over all the triangles of the canonical forms for all the triangles. Okay? That's not 100% obvious. That is not 100% obvious.
Why did the singularities along the internal edges cancel?
Exactly. Yeah. So why do the singularities cancel? So the whole point is that in this triangle, as you say, this triangle has a pole there and there, which is good, but it has a pole there, which is bad. So does this one, right? But why is it guaranteed that those poles cancel? It's guaranteed that they cancel precisely because each one of these forms is a canonical form for the triangle. So the residue on that line is just something fully determined by the fact that it has singularities at the two edges and nothing else, right? And therefore, the residue from the other side is exactly the same. Right? And now it's only an issue about the sign. So you have to believe me that the sign cancels, but it's not. And so here it's for triangle where it's easy to see. But let's say I did something more complicated. I literally took that square. Okay. So the sum of the canonical forms of these guys also has the feature that the canonical form, that the pole on the inside cancels. Okay? And even if you do something more complicated, this is a slightly more interesting example, because here I'm claiming that this plus this plus this has no form on that edge. But it's not the case. I mean, if I take this piece, that piece does indeed have a pole out here, right? It's not that it only has a pole in here, right? This piece has a pole everywhere on the whole thing. Okay? But still, it's easy to argue recursively that by the property that the lower things are that you get canonical forms on their boundaries, that any triangulation gives you a canonical. Any geometric triangulation gives you a formula for the canonical form. There's not 100% obvious statement, but it is true, and it has a simple but not 100% trivial recursive proof. That's not just for polytopes, but for general positive geometry. It's not quite defined yet. So this is a useful thing. If you have a complicated positive geometry, you can break it up into simpler ones, and in that way get the canonical form. Okay? Now, this should remind you of something, right? This kind of looks like the canonical form. I mean, it kind of looks like a volume, right? The forms have similar additive properties to volume, right? I take the canonical form for two things. I put them together. I get the canonical form for the whole one. Okay. So here is the final fact about canonical forms. And everything I told you so far, I've only illustrated with polygons, and they're true for general polytopes. But they're also true in all the fancier examples, like amplitahedra and the Grassmannian generalizations of polytopes, which we probably won't have time to talk about. But it's true for all of them, including this business about triangulation. This last thing that I'm going to tell you, we only know how it works for polytopes, and in few cases where we generalize away into Grassmannians, but definitely not in general. And I think it's one of the big open problems in this entire subject. Okay? But let me first tell it to you to define the appropriate generalization of this notion. But what I'm about to tell you really explains why this thing has the property of looking like a volume, because in fact it is a volume. Okay? But let me explain why it's a volume. So in order to do that, let me go back, and for the moment, let me remind you of something, which is the high school formula for the area of a triangle. Okay. Now we're going to talk about the areas of triangles, and if someone hands you a triangle whose vertices are, I don't know, x1, x2, and x3, then the high school formula is 1/2. The ones I put the 1/2 because I don't want to give you the impression that I don't remember the formula for the area of the triangle. Okay, okay, it's 1/2 times that determinant. Okay, so it's x1 minus x2 cross x1 minus x3. There's many ways of writing it. Right? Okay, so so how do I say that formula projectively? So the notion of area. The notion of area has units, right? So it's not perfectly projectively well defined, but we can go pretty far. So we imagine that there is some line at infinity here, right? So in order to just draw this picture, we have to have some line at infinity. Okay? So there's some line at infinity. I can call that. Let me call that W. Well, let me call it Y. For a reason that'll become obvious. So y would be 1, 0, 0. Ignore for the moment that I was calling y a point a moment ago. So just ignore everything I was telling you a moment ago. So if I do this, then the way to write this formula for area is this determinant is of course nothing other than if the coordinates are the vertices are x's, that's just this big determinant, x1, x2, x3. Okay? But now for this to make sense projectively, I have to have x1y, x2y, x3y here, right? Now this has vanishing weights in all the x's. Of course, it has an overall weight minus 3 in y, and that's just life. Area has units, right? That's just life. So that's the formula for the area of a triangle, where I think about y as giving me the plane, the line at infinity. So y is the line at infinity, and so that's the area. Okay. Okay. Now, what if I had given you, instead of the vertices of the triangle, what if I had given you the edges? Okay? If I give you the edges, so I call the edges now 1, 2, and 3, or let me call the edges A, B, C, right? Then, well, we can figure out what the area is, right? So, by the way, remember, these are all 1, right? I mean, in our usual coordinates, these things downstairs are just 1, and that's why it's just the same formula.
That's a round parenthesis rather than a bracket.
Sorry? That's right. This just round is just a dot product. So the downstairs index and then upstairs index, right?
So you're saying that y is in the dual space.
That's right. Y is in the dual space. That's right. So x's are so y is a line, x's are points. Okay. So now I just want to rewrite. I want to write the formula in terms of the data. If you gave me the edges instead. Okay. Well, that's very simple because x1 is just the intersection of a with b, x2 with b with c, x3 with c with a, and so on. So there's only one formula thing it could be. It's just ABC squared over, now it's these epsilon brackets, YAB, YBC, YCA. Okay? Now I want you to notice the similarity between this formula and the canonical form we had for a triangle. Okay? See, what we had before was a picture of points A, B, and C, and a point Y, And the form that we wrote down was 1 over YAB, YBC, YCA. And then we had exactly this ABC squared. And of course, to make it a form, we put a YDY. Okay? But you notice that this part of it looks exactly the same. It's just that here they're points and there they're lines. Okay? So we see what the relationship is. The canonical form is equal to this universal thing that's there in everything, YDY, times the area, not of the polygon, but of the dual polygon, where Y is interpreted as a line at infinity instead of a point. Is that clear? That's pretty cool, right? So there's this relationship between the canonical form of, and now it's in general true for any polytope, so let me just say the claim. There's a formula that the canonical form of Y in a polytope P is equal to Y dy dy, or Y dny in general, in any number of dimensions, times the volume of P dual, with Y being the hyperplane at infinity. Okay? Now this is the most satisfying, and so I mean I could say this in many ways. So here's the formula for the canonical form. So I can say omega is Y dy dy has an integral over the dual space W dw dw, let's say, divided by W dot y cubed, if I'm just doing polygons, but where now W is inside P dual. Okay. Or if you like, there's one huge form on the space and the dual space, Y and W space, this trivial form, Y dy dy, W dw dw, but I integrate over half of it to get the canonical form on the other one. Okay. This is a very satisfying formula, because from this formula, you can derive that it has logarithmic singularities in Y. And I won't do that, but you can really understand all the properties that the object has very beautifully. This is clearly the most invariant way of expressing the information about this canonical form. Okay? And I should tell you, it's also, well, I want to, yeah. So, triangulations, so I told you that you can get the canonical form by summing over a triangulation of the polygon. The reason this is true, it's a very well-known fact that triangulations of a polygon also give you a triangulation of the dual polygon, although it could be inclusion-exclusion, it could be pluses and minuses, but all the signs work out. So the triangulation of one gives you a triangulation of the other. So the fact that you triangulate the volume is trivially true, and that translates into the fact that the canonical form will have that property, and so on. Okay, so this gives you a final bit of intuition that we can think about. So in this sense, we can think about the canonical form as the volume of the dual object. Okay. What we don't know how to do is define this dual amplitude, for example. Okay, so we have everything, all the rest of the stuff goes, there's positive geometry, there's forms, all the rest of it go, but we still don't know how to generalize this notion of a dual. And there's many ways of deriving the statement that I mean, I gave you just an intuitive reason to see that it's true at the level of simplices. But in fact, there's really a straightforward derivation to go back and forth from one to the other that involves Fourier transforms or Laplace transforms in a very simple way. And it's clear that the obstruction to doing this for the Grassmannian generalizations is because there's some nonlinear version of a Fourier transform involved. We don't know how to do it. So, but there's many reasons to suspect that such an object exists. I don't have time to tell you, but there's lots of circumstantial evidence that there is a dual amplitude, but we don't know. Or there's the notion of a dual positive geometry is there in general, but we don't know. All right, so those are all the things that I want to tell you about positive geometries and their canonical forms, just illustrated for the case of polytopes. But that's enough for us to do now. Go back to physics and do our first example. The first example that connects these things with physics. And it really is the absolute simplest set of scattering amplitudes that you could imagine. So this is part 2. we have phi cube theory scattering amplitudes. And the associated. Okay, so let's imagine that we're just, so in general, the data you need to label a scattering product, you have to give me momenta, on-shell momenta, and you have to give me the spins of the particle. If we have massless particles, they only have helicity. So you have to say a helicity, if you have a photon or a gluon, they have helicity +1 or -1. A graviton, +2 or -2. A scalar like the Higgs is just 0. Okay, so the scalar is the easiest case. So let's just imagine we just have scalars. Okay, so things like Higgses. So we want to do scattering amplitudes for scalars, and so the absolute simplest scattering amplitude you can imagine is for 3 particles. And here the amplitude is just a constant. There's nothing it can depend on, right? I have 3 momenta, P1, P2, P3, right? P1 plus P2 plus P3 equals 0. And the only invariants I can possibly have, things like P1 dot P2, well, all these things are equal to 0, right? If all the particles are massless, all the P squareds are equal to 0, then all the invariants are 0. So there's nothing for this amplitude to depend on. There's no analog. When you go to higher points, we have interesting invariants. So the 3 particle amplitude can just be a number. That's the strength of the interaction, so we can call it G. Okay? There's nothing to say. Now we want to start calculating 4 particle amplitudes. And so all we do is we imagine that this particle has momentum P1 and P2. So this internal thing has momentum P1 plus P2. And so we just write down a factor of 1 over P1 plus P2 squared. Okay? Or if I drew this diagram, 1, 2, 3, 4, I'll write down 1 over P2 plus P3 squared. And therefore, for every diagram that I draw, these are the Feynman rules. They're as simple as possible, right? So if I just draw trivalent diagrams like this, for every diagram, I just have 1 over the product of the propagators associated with each one. Okay, and the amplitude is what I get by adding them all up. Okay.
I lost track. Write a formula.
Yeah.
Summations of products.
Yeah. So for example, if we do the next, so in fact, let me simplify. Let me imagine that my
That can go.
Can I erase this? Okay, thank you. So let me imagine that my particles, let me imagine there's an ordering to the external, there's an ordering to the label, then I'm only drawing planar graphs, just to make my life a little bit simpler. That's a story that will be associated with the icosahedron, and then there are generalizations that are generalized things, permutahedra, more other objects. But if we just have an ordering, then I'm just going to draw, for example, at 4 points, I would draw 1, 2, 3, 4. And these are the only diagrams. At 5 points, I could draw 1, 2, 3, 4, 5, plus its cyclic rotations, right? So here I would write 1 over P1 plus P2 squared, 1 over P1 plus P2 plus P3 squared. Set, right? Now notice, of course, I could write this as also as P4 plus P5 squared, because I have momentum conservation. So there are many ways of writing. At 6 points, we have this Mercedes-Benz diagram as well, together with the other ones, and so on. Okay, so we have okay, so that's it. That's what the amplitude is, and so I'm restricting myself again just for simplicity to summing all cubic diagrams, trivalent diagrams, planar with this ordering 1, 2, 3 up to n on the outside. Okay, so is that clear? All right. Now, so let's clean this up a little bit so that we introduce a nice notation and we can think about it easily. So for this problem of, so that's the physics that we want to talk about. And then we back up a second. So here's the problem, there's no spin even, right? So what do the amplitudes actually depend on? So what is the space of things they actually depend on? They don't even depend on the momenta individually, because they can only depend on Lorentz invariant dot products of momenta, right? So item number one is to figure out what is this kinematical space. So there's a kinematical space of things that just depend on these dot products, pi dot pj, right? And so the very first thing I want to do is just understand what that space is, okay? Because that's clearly very redundant. I can't give you, if I want to specify some momentum configuration, if I give you all the dot products, that they have lots of relations that they satisfy and so on. So let's first figure out even what is the dimensionality of space count, get some feeling for what's going on. Now, something else to notice about these simple scalar theories is that these theories don't actually know anything about the number of dimensions of space-time that they live in, right? No, however many dimensions you had, you'd have exactly the same formula. So in other words, if you're in 4 dimensions, if you give me, 6 momenta, they're all linearly related to each other. So there's some fact. If I give you all the dot products between them, they're going to satisfy some extra relations due to the fact that they live in 4 dimensions, right? But none of those things matter in these amplitudes. And so to make our life really simple, we're going to imagine that we're in infinitely many dimensions. So we don't care. We don't care about the constraints arising from the fact that the momenta are themselves finite dimensional. Okay? So we just want to count what are all the kinematical invariants that you can have. What are all the possible dot products that you can have? But the only constraint that we have to satisfy is momentum conservation. Okay? So if we just count the dimensionality of this kinematical space, so let's call this kinematical space Kn of these pi dot pj's. But what is the dimensionality of this kinematical space? Well, there's n choose 2 p's that I can take to be a dot product, pi dot pj, right? But they satisfy a constraint. Because the sum of all the pj is equal to 0, this is momentum conservation. So if I dot this, pi dot this, that's also equal to 0, right? So this tells me that the sum of j of pi dot pj is equal to 0. So for every I, there's a constraint of this form, okay? And therefore, the number of invariants I have is n choose 2 minus n, which is n times n minus 3 over 2. Okay, so let's see. When n equals 3, it's 0, which is correct. So that's what we saw. There's no kinematical invariance at all. When n equals 4, the answer is 2. And those are the familiar Mandelstam S and T variables, if you're a physicist. Okay? Right? Yeah. When n is 4, this is 2. 4 times 1 over 2. Okay. When n is 5, this is 5, and so on. Okay. Okay, so now, because we have an ordering for the particles, it's actually natural to visualize momentum conservation by drawing the following polygons. So imagine, draw the momentum P1, P2, P3, the vectors n to n, then they'll give you a closed polygon, right? Because all the momenta add up to 0. If you didn't have an ordering for the particles, it wouldn't be natural to draw. You have to choose an ordering to draw this, but we have an ordering, so this is a reasonable thing. It's a reasonable thing to do. Okay. And now notice that associated with every diagonal here, there's a natural object, just P1 plus P2 up to that P all squared, right? 2 adjacent ones is 0, because P1 squared is 0, geometrically with massless particles. But I can have P1 plus P2 squared, P1 plus P2 plus P3 squared, and so on. So if I go in general from some I to some j, there's a natural variable xij, which is pi plus dot 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 plus pj minus 1 all squared. Okay? So that's just some linear combination of the pi dot pj, right? There's well, something that's very convenient about this is how many of these x's are there? There's exactly as many of these x's as the dimensionality of kn, right? Because the number of these diagonals is also n choose 2 minus n, for a very obvious reason. Okay? All right, so these x's are a great basis for all the kinematic invariants that I can build. Okay? Furthermore, in terms of the x's, it's even prettier and easier how to just write down the formulas for the amplitude. Okay, so let me go back to 4 points. I had these two diagrams, 1, 2, 3, 4, and 2, 3, 1. These two F and P channels. So this was 1 over P1 plus P2 squared. And this is 1 over P2 plus P3 squared. Again, always there's the annoyance that I could have meant P3 plus P4 squared. I could have meant, right? But what is this in terms of this picture, right? In terms of this picture, the propagator that makes an appearance there is exactly that guy, right? So this is 1, 2, 3, 4. And of course, what's nice is when I write it like this, automatically, I don't have to say it's 1, 2, or 3, 4. It's just that diagonal, right? So it's 1 over, so this is 1, 2, 3, and the other, so these were the momenta, right? These were the labels, P2, P3, P4. I can rewrite this also as 1 over x13, associated with that picture, right? And similarly here, this is 1 over x24. Okay. Now, what do I get at 5 points? At 5 points, I have, 1 over P1 plus P2 squared, P1 plus P2 plus P3 squared. Okay, so who are these in my picture of the polygon? Now I have 1, 2, 3, 4, 5. 1 over P1 plus P2 squared is that x. And 1 over P1 plus P2 plus P3 squared is that x. Okay? So every Feynman diagram gives me the product of x's of some triangulation of the polygon. The fact that it's, and of course, the diagram here is just the dual of this diagram, right? Okay. So instead of drawing cubic graphs, I can just draw some triangulation of the polygon, any old triangulation, and the product of 1 over x's for that triangulation of the polygon is the result that I get from that Feynman diagram, right? So now we have the sort of cleanest way of saying what the sort of Feynman diagram calculation is, if you like. Okay? So the amplitude, so we have our our kinematic space. Our kinematic space variables are just the xij, beautifully, right? For non-adjacent ij, right? So by convention, we say xi I plus 1 is 0. Okay? Okay? And the amplitude is equal to the sum over triangulations of the product of 1 over the xij's for ij in the triangulation. Is that clear? So so we've just rewritten the Feynman rules for this theory, just in terms of triangulations of a polygon. Is this clear? All right. So far, nothing exciting is happening. I mean, this is all. Everything is planar, so obviously we have dual diagrams and triangulation of the polygon. These things we've known since time immemorial. There's nothing to it. And this is also why from essentially the moment that my friends and I knew anything was relating polytopes and positivity and geometry and amplitudes, you know, we know that the icosahedron is famously associated. One of its presentations is in terms of an object whose vertices are triangulations of a polygon, and so on, right? And that the icosahedron has the magical feature that the faces of the icosahedron factorize into products of lower icosahedra. Okay, so we'll review all these things and discover them again in the language, in some slightly different language in a moment. But it was sort of clear that we wanted to somehow connect with the icosahedron to the amplitudes for this theory. And it was an endless source of frustration that it could not be done in any precise way. Okay? So it was very strange. We could do these much fancier things for n equals 4 superhanging middles and the amplituhedron and these Grassmannian generalizations of polytopes without being able to do this simple case. But it's because there was a conceptual thing missing. There was a simple but important conceptual thing missing, which I referred to earlier, is this idea of how we see all this geometry, not in auxiliary spaces, but directly in kinematical space. Okay? And you can see what the challenge is, right? Because I've given you a story. I've given you a story that here's the kinematical space. It's pretty high dimensional, right? It's n minus 3 over 2 dimensional. Somehow, you want to think about Feynman diagrams as somehow triangulations of this, and that's also what it looks like, right? You know, so you want to think about each diagram as giving you a piece of something. You want to sum them all up. But it's clear that we have at most, well, we have n minus 3 poles associated with each term. So each term is something that at most has kind of n minus 3 faces, maybe it's a simplex something, but it's n minus 3 dimensional. But the whole space is n minus 3 over 2 dimensional, much higher dimensional. So in what earthly sense are they combining or gluing or into some geometry? That was the sort of basic challenge. Okay, so it was not clear the sense in which these Feynman diagrams were tiling something. Whereas in other contexts we understood, in these more fancy, sophisticated contexts, we really saw that representation of the amplitude should be thought of as a triangulation of the positive geometry. Okay? But here, there's this very basic mismatch between dimensions. But the kinematical space is incredibly high dimensional. We had to find, and yet the sort of pieces seem to live in something lower. And it was by a very circuitous path that we had a picture of the amplituhedron that did not live in kinematical space, it would meant other particles, it lived in some auxiliary Grassmannian space. But after a long time of trying to describe it much more intrinsically, we found how to represent it directly in kinematical space. However, the representation involves this novel idea, whose sort of general structure I'll give you, but then we'll illustrate it in this simpler example of the icosahedron. Okay? But just before saying a few other things, let me just tell you where we're going. We're indeed going to see that these amplitudes are the canonical form of something. That there's a differential form that lives on kinematical space. The differential form is the canonical form of an icosahedron. But the icosahedron does not live, has the wrong dimension. It doesn't live in this giant kinematical space. But there's a natural family of subspaces that live in this huge space on which you see the icosahedron. And this canonical form, which is defined everywhere, has the nice feature that when pulled back to one of these subspaces, it becomes the canonical form for the corresponding icosahedron geometry that's revealed there. Okay, so that's the sort of general idea. I'll say it in a little more detail in a moment, but just to say a few other things, just as a motivation to tolerate some of the next 20 minutes or so. We can think of Feynman diagrams as one of the triangulations as one triangulation of the icosahedron. There's a relatively nice natural triangulation of the dual icosahedron, but there's a relatively nice triangulation of the icosahedron. There are many others. Okay, and furthermore, it turns out that the amplitude actually has a hidden symmetry, which Feynman diagrams obscure. Each term in the amplitude breaks that symmetry. Only the full sum has it. Okay? And this triangulation of the icosahedron obscures the symmetry, and other ones make it more manageable. So even something as seemingly dull and boring as this phi-cube theory has hidden symmetries that are only visible when you see the underlying geometry. And the Feynman diagram expansion breaks it. And the most amusing thing, one amusing thing is that this is a perfectly nice canonical triangulation. There are other smaller triangulations. So there's in fact more efficient formulas even for this dumb phi-cube theory. Something I never imagined you could do any better than Feynman diagrams for something as dull as this. Even this, there are things where there are shorter formulas And the short, it doesn't matter that much, but there are ways of expressing the answer that manifest more of the properties term by term than we see here. So that's where we're going to be. That's where we're going to be heading towards. Okay, but just to sort of repeat the big picture, and this big picture is in common now with all the examples. I mentioned the icosahedron, cosmological polytopes, and the amplituhedron. In all cases, there's a story that roughly looks like this, and now is the kind of beginning of an answer to the question directly in the kinematical space where particles live. What kind of question should we ask? So there's some big kinematical space, K, and it has some big dimension, capital D. The key idea we're going to see is that we do not think about scattering amplitudes as functions. Okay? We think about scattering amplitudes as differential forms. Now, I already told you about canonical forms associated with positive geometries. In all of our previous understanding, there was always this form lying around, and then there was always some dictionary to get a function out of the form. Okay, the actual amplitude you could ask an experimentalist to measure. Okay? One of the novelties of what we've done is realize that the amplitude is a differential form. It's actually more naturally thought of as a differential form already. A differential form in this kinematical space. And we'll see how it works very explicitly in this example. But we're looking for a little d form, where little d is in general smaller than capital D. Okay? And here's what determines, here's the sort of big picture for what determines this form. In this big kinematical space, there's going to be some positive region. So there's going to be some positive region P. I'll draw it. I mean, in general, all these things are curvy. And for the icosahedron, they're all determined, cut out by linear equations. So let me just draw it in a curvy way. So there's some positive region P. It's space-related. It's top dimensional, right? So, but there's some things that are in it and not in it, right? So there's some good part. There's some good part of kinematical space. So this is capital D dimensional. There's also, however, a family of subspaces. A whole family of subspaces. There's some family of subspaces, natural, which have dimensionality little d. Okay. And geometrically, they have the property that these subspaces intersect the big positive region in now a little d dimensional positive geometry. So this intersection of SD with P is a positive geometry. Okay? And this differential form that lives everywhere, okay, lives everywhere in the big kinematical space, it has the feature that when you pull it back to that subspace, so the pullback of this differential form to the subspace, so omega d on SD is the canonical form of, let's call this positive geometry P, little p, or P little. Okay, so that's abstractly what's going on. Okay? So we start to see how in the seemingly dull space, right, nothing's going on, just a space of kinematics momenta, where's all the magic of physics and amplitudes and locality factorization? Where's all this stuff happening? It's coming in some as we'll see, rather natural choices for what capital P is, what these subspaces are, this kind of question. But it's very important that we think of amplitudes as forms, because that is what allows us to see geometry directly in kinematical space. If you have a form, then it makes sense to take a residue of a form. And as we've already seen, there's a connection between geometry and residues. I can't take the residue of a function. I need a form, okay? And so that's the beginning of, yeah, that's the kind of thing that we're after.
So what is the MD here?
Sorry? Well,
Capital D is n minus 3 over 2.
yeah, so we'll now do our example. So big D is n minus 3 over 2. Little d is going to be n minus 3. Okay. And so let's let's build up to it. But so I won't jump straight to this picture. I'll sort of build up to it by motivating what this form is, and then we'll.
Let me intervene briefly.
Yes.
only because I have to catch a train.
Okay?
It's been great to have you here. Please come back as
Oh.
soon as possible.
Thank you, thank you.
And we will continue the discussion by email and Skype and whatever.
Perfect. Thank you so much for the invitation, Jim.
Oh,
Really,
my
really
pleasure.
good. All right, yeah.
So I guess it's now officially turning from a deformation seminar to an outfitting seminar.
All right. Okay.
Oh, how about people?
So let's go back to this example. And let me even revert in this case just to the usual variables. Oops.
I will be back with some paper
Oh,
towels.
no, we'll take care of it, Jim. Don't worry about it.
Okay.
Don't worry about it, don't worry about it. No one's worrying about it, right? For normal amplitudes, people, maybe with these variables, you write down 1 over x plus 3, 1 over x to 4. There's only one propagator here, right? So obviously, you're tempted, it has, it all looks like 1 over s. If I want to make a differential form out of it, you're actually tempted, what would you be tempted to do? Instead of doing this, you want to write down like ds over s, okay? And dt over t. That's much nicer, d log s, d log t. Very good, okay? Now what about that plus sign? Okay, so this is one of the slightly cool things. There actually has to be a minus sign there. So there's now a choice of signs. But now let me justify the minus sign, or justify why you'd want to put a minus sign there. So something that we think is that in physics only ratios matter. Overall scales don't matter for anything, right? So you would like this differential form only to be a function of the ratios of s and t. Or said another way, you want the form to be well defined on the projectivized ST space, right? Because the overall scale shouldn't matter for anything. If I put a plus sign there, it's not true. It's not projectively well defined. So with a minus sign, it is. Okay? With a minus sign, this is equal to d log s over t. Okay. So again, so is it clear what it means to be, so is it clear why with a plus sign it's not true? For something to be projectively well defined, it has to be invariant under ST goes to any function of ST times ST. Okay. When the differential forms on projective spaces, it has to be invariant under the local version of the GL transformations. Okay. And so if you put a plus sign, this is not true. But with a minus sign, it is. Okay. And of course, this presentation makes that manifest. Okay? All right, but with that rule, you see, you can now build an n-3 form associated with every Feynman diagram. Okay, every Feynman diagram, you just put the wedge of the dS's for all the s's together, right? And now it turns out that demanding that the form is projective completely fixes all the relative signs. Right? And there's a unique up to overall sign. There's a unique form that is projectively well defined. Okay. Yes.
So one question, I would just intuitively think that the modulus squared of the amplitude
Yes.
is more naturally a differential
Yes.
form, right? Because it's basically a probability measure. But
Yeah.
here you're saying it's the amplitude itself.
Yeah, that's right. And this is actually, it's a very deep question, and I can come back. I don't have that much to say about it, but it's related to many other somewhat mysterious things. So you're right, but you also have, yeah, let's return to that question later. It's a very important question, but yes, indeed. I mean, you might have naturally thought, they might have thought similarly. Anyway, there's a variety of kind of squared objects that you might more naturally think are associated with forms. Here it's the amplitude itself for like planar looking things that are associated with the forms. So yeah, let's come back to that question later. But anyway, I'm just telling you a rule, right? So just first, there is a nice differential form that's associated with, instead of looking at Feynman diagrams, with each one I can take this form. Okay? So now we have a form. Now we have an n minus 3 form. If we have n points, we have an n minus 3 form. We have some omega n minus 3. And now we have two questions. Question one, how do I get the actual amplitude from the form? Right? In the end, I do want to get 1 over s plus 1 over t. That's what you actually measure. Okay? That's what you see. Where is that information? Here. That's question one. And question two is, how do I get the amplitude from the form? And question two is, what does any of this have to do with geometry, positive geometry? Where's the positive geometry? And the answer to both questions is the identification of some interesting subspace in kinematical space. So let me explain how this works. Before telling you how it works in detail, let me just illustrate how it works in this simple example. So in this simple example, I have ST space. So first of all, I have ST space, or XS, or X13, T, or X24. And before saying anything else, I just have the whole point. Okay? Now, if we've seen sort of anything, we know to expect that the poles of the form or whatever should correspond to boundaries of the geometry. Okay? So that makes it very natural to look at the region where S is positive and T is positive, right? But then that puts boundaries at S equals 0 and T equals 0. Okay? So this is the positive region in this case. That's that big P that I was talking about. It's just that two-dimensional positive. Okay? But still, we have a 2 form. Oh, we have a 2-dimensional space. We have a 1 form. We have a 1 form, which is ds over s minus dt over t. Okay, so, but now we're going to actually look at a family of 1-dimensional subspaces. Now, here it's sort of obvious. There's not much you can do. We look at the 1-dimensional subspaces that look like s plus t equals a constant. In fact, I'm going to demand that that constant is greater than 0. If I didn't, of course, this wouldn't intersect anything, right? So, but on that subspace, s plus t equals constant, first, what does it look like? So it's a line here, right? It's a line where the intercept is c. Okay? So, first of all, the intersection of this subspace with my positive space is a little, rather trivial positive geometry. It's an interval. Okay? Is that clear? Now, what is the pullback? What is the pullback of this? Okay. Now, first of all, you see, because on the space s plus t equals a constant, omega 1 pulls back to s plus t equals constant is just ds times 1 over s plus 1 over t. Right? Because dt is negative ds on the subspace. Okay? So you see, after factoring out the universal thing that's there, that's the amplitude. Okay, so the amplitude is revealed on the subspace. And note, it's a whole family of subspaces. So, so I get I probe all. It's not like I'm only probing the amplitude on some codimension 1 surface. There's a whole family of these guys. And so I do get the expression for the amplitude everywhere. And a big region that can then continue anywhere you like. So first of all, that's the amplitude. But secondly, also this omega is the canonical form for this dumb interval. Right? The whole point is, it's built so it only has poles when s goes to 0 and t goes to 0. Right? With the minus sign, there's no other pole. And so here's the pole where s goes to t goes to 0, there's the pole where s goes to 0. Okay? So it just has canonical logarithmic singularities at the boundary. Okay? So this is the idea that we're now going to generalize. Okay? We're going to find a natural positive region. That's very obvious to guess, and we're going to find a natural choice of subspace. And in both cases, you see that there's essentially nothing else you can do. There's no other natural choices that you can make for them. But what we're now going to discover is that the subspace and the big positive region of the subspace actually produces the association for us, and it produces a realization of the association that's not identical to one of the ones that mathematicians have. One of the many of the ones that mathematicians have come up with over the last 50 years since Jim's original work. It's very closely related to some of them, but it's not identical. Okay. So let's now talk about, yes.
Is there anything physical associated with the choice of C?
Huh?
Your constant C, so it's
No.
completely arbitrary.
That's right. It just has to be positive. It just has to be positive. There's a whole family of them, and so for anywhere you choose this, yeah. Yeah. Okay. So now let's see the icosahedron in kinematical space. So first we have the positive region. So we have this big positive region P, and here's obvious what it should be. It should just be that all these x's are positive. Okay, so I have nn minus 3 over 2 x's. So there are nn minus 3 dimensional x's, and so this is the positive octant, or whatever you call it, in nn minus 3 over 2 dimensions. Okay? Okay, but now, see, notice what I've done here. What I've done is in this picture of the polygon, this involves a choice of two vertices. I choose an I and a j, and for every I and j, I'm making a statement. Okay? Now the subspaces turn out to be associated with a choice of edges. Let's say I choose an edge here, from I to I plus 1, and I choose some other edge here, from j to j plus 1. Okay? For every choice of edges, I'm going to impose a constraint on the variable. So what I'm going to do is take this momentum, pi, and that momentum, pj. Okay? So my subspace is going to be cut out by the condition that -2, just to make life easier, pi dot pj is equal to a constant Cij. Okay, and I'm going to assume that that constant is positive. Okay. Now, I told you that the x's are a basis, so I should be able to say the statement in terms of the x's. Okay? So let me tell you what the ultimate statement in terms of the x's is, because it's even prettier and nicer in terms of the x's. So now this is still with the subspace. The condition is that for every I plus 1, the little few caveats that I'll mention, for every I plus 1, jj plus 1, you look at the following. You look at the following picture. So the statement is that the two crossing diagonals, xij plus xi plus 1, j plus 1, minus the non-crossing diagonals, xi plus 1j minus xij plus 1, this is equal to Cij, which is pi. Okay? That's it. Now, little caveat, I and j cannot be adjacent. So first of all, ij non-adjacent. If I and j were adjacent, this would be impossible, right? Because if I and j are adjacent, I would be left with just one of the things which is negative. So I can't do this for the I and j that are adjacent. That would be inconsistent. Okay? So I and j can't be adjacent. There is a second caveat. Okay? which is, notice that this formula looks like in the I variable and the j variable, it looks like a discrete derivative, right? So there's an xij minus xi plus 1j. Or the other one is xi plus, anyway. So it's a discrete variable in both I and j. Therefore, if you sum over all j, you get 0. Okay? So I can't literally say this is true for everybody. If I say it's true for all non-adjacent ij, I would get a contradiction. I can't make them all positive. So that means I have to throw one of them out. It's a chain, okay, and I can't close the chain. So that means that I cannot use n1. So I have to choose one of them. By convention, I'll call it n1. Okay. So for all things like this, except one of them, except one, which I can take to be n1. So I never use n1. Okay. But for all the rest of them, I impose that constraint. Right. Now you can count. If you count how many of them there are, it's exactly the right number, so that with all these conditions, we're left with an n minus 3-dimensional subspace. Okay? So it has the right dimensionality to cut things down to n minus 3 dimensions. Okay, but anyway, that's it. So here's the space that I'm talking about. I'm describing it as embedded in this n minus 3 dimensional 2 space, but it's really n minus 3 dimensional. And it's the intersection of these hyperplanes with this positive quadrant. Okay? And now I claim that this object is a representation of the isosahedron. It's a particularly nice representation of the isosahedron.
Okay. And so like the meat is then transforming this dot product in the momenta to the from the piece of the x.
Yeah, I mean, if this looked nice to you, yes, that's the meat. I could have also just written something like this down to begin with. Okay, so this, but yeah. So, but the meat, one way or the other, is being able to identify a simple subspace like this. Okay, and now the magic is that now I'll show you why this geometric space. First of all, it's the isosahedron, and secondly, how it captures all the physics of factorization, unitarity, locality, and so on. Okay? So locality here is being put in relatively trivially from the fact that all these x's are positive. Okay? But now the magic is that this simple subspace is going to cut out a shape which has the structure that when we go to the boundary, it factorizes into lower objects of the same form. That's not super obvious, right? That's not yet super obvious. Okay. Okay. So this is, so again, let me just summarize this together with xij positive. And now I want to show that this is an isosahedron. And if you don't know what an isosahedron is, then we'll see naturally what its definition. Okay. So the claim is that this is an isosahedron. But let's see why that is. So what I want to do is see, I've defined this space now, I want to see what its boundaries look like. Okay? So what do the boundaries of this thing look like? First, what do the codimension 1 boundaries look like? The only boundaries we have are coming from the only inequalities, this is a fixed subspace. I'm forcing the constants to be positive, just tell me which subspace. But the subspace is fixed. The only inequalities we have are on the x's. So the only time I can hit the boundaries is when one of the x's goes to 0. Okay, so let me take one of the x's to 0. Some xij. This xij goes to 0. Okay? Now I want to go to the next codimension boundary. I want to put some other xij to 0. Okay? But I'm now going to show you that it is impossible to put any other xij to 0 that crosses the original one. So let me prove that. To do that, let me go back to this basic inequality and derive a consequence from it first. You see, this is an equality that's true. So let me draw one of the challenges in this subject is that to draw something generic, you have to go to an octagon. It's hard to draw, but I don't even know if that's an octagon. But anyway, so you have something that involves adjacent guys. So here are some I plus 1 and some jj plus 1. Okay? So we're making statements about these quadrilaterals, like this plus this minus that, right? But because this looks like a discrete derivative in I and in j, if I sum this formula from I equals some little a to little b, let me sum this formula from some little a to some little b in I. And I sum it from some capital A, from some capital A to capital B in j. Okay? Because it looks like a discrete derivative, the formula is exactly the same, now just for this bigger quadrilateral. Okay? So in other words, for every quadrilateral, not just the ones made out of the adjacent ones, but for all the other quadrilaterals, it's true that the sum of the two long ones minus the non-crossing ones has got to be positive. Okay? Is that clear? That's a consequence of the elementary one. Why didn't I add all of them by hand as these in my definition of subject? Because if I made the constants independent, that would be too many constraints. Okay. So I use the elementary ones, which give me exactly enough constraints to go down to n minus 3 dimensions, and the rest of them are consequences. Okay. So, but it's nonetheless true. That the right-hand sides of all these are positive because the c's are all positive. Okay? So for every quadrilateral, this plus that, the two longs minus the two shorts are positive. And now you see why, if you put one of the ones to 0, you can't set another one to 0. Okay? A crossing one to 0. If you did, there would be a quadrilateral in the problem such that the two longs minus the two shorts would be positive, but the two longs are already 0, so something negative would have to be positive, and that's impossible.
You're summing over the i's and over the j's?
Yes, I'm going to sum over the i's that run from little a to little b, and the j's that run from capital A to capital B. Okay? And because these sums telescope in both I and in j, because this looks like a discrete derivative in I and a discrete derivative in j.
I'm just trying to
Yeah.
figure out what would be the constant of the right side.
Oh, it will be the sum of all the CIJs for all the will be on the right hand side of the sum of all the. So this would equal.
Pairwise CIJs.
Yeah, all the pairwise CIJs. That's right. The sum of would be the sum of all the CIJs for I between A and B and J between exactly capital A and capital A. Okay. Okay, so that's this crossing business is the magic, which tells you that if you set one thing to 0, the next boundary I can't set a crossing one to 0. Okay, so what can I do for the next one? Well, I can do that. What can I do for the next one? I can do that, and so on. Okay, so all the boundaries are associated with partial triangulations of a polygon, and finally the vertices are a complete triangulation of the polygon. Well, that's the association. Okay. The association is the object whose vertices are triangulations of a polygon and whose facets of intermediate dimension or coarser triangulations of the polygon, with inclusion defined in the obvious way when you refine an existing triangulation. Right? Okay. But we've discovered it in kinematical space. Okay. And furthermore, we've given it a polytopic presentation from the get-go. So what was remarkable about what Jim did when he discovered I was hoping to hear more about the history from him, but what I understand of the history is that he actually, it's very non-trivial, purely combinatorially. Someone hands you triangulations of a polygon, and you say, you can certainly make a list of objects. You can call them vertices and edges and faces if you want, just as a notion of inclusion, right? But it's not at all obvious that there's a geometric object that represents those as facets, right? So Jim discovered that such an object exists, but it took a number of years before people realized it could be actually described polytopally. And his original presentation actually had curvy had curvy faces. Okay? So it took, I think, 3 or 4 years before people realized how to cut out the icosahedron with linear inequalities. Okay? So it's not obvious a priori that any such thing was possible at all, and never mind that it can be cut out by a polytope, by linear equations. But the association that we discovered in kinematical space is automatically polytopal, and I think is a particularly nice and symmetrical presentation. There are zillions of polytopal presentations of association, but I think this is not trivially one of the ones that's in the literature anyway. It's slightly different than some of the other ones. Okay, so this is a geometry sitting in Mandelstam space, right? That's the sort of cool thing, is that it seems like it's empty, inert, boring space, and you have to put a little bit of structure in by hand, a little bit of positivity. You have to make some guesses about these x plus x minus x, but you have to sort of look a little bit for interesting subspaces in this otherwise boring seeming space. But then these wonderful geometries emerge. And now I can just tell you the claims, right? So now we've discovered this association. And now I claim that form that we talked about, the Feynman diagram form with the signs and everything, then it has the feature universally for all these subspaces. You pull it back to the subspace, and all the signs disappear, just like we saw for the 4-point case. You pull off some universal piece of the subspace, and then you get all plus signs. So you get the sum of all of them. And that's how you read off the amplitude on the one hand. On the other hand, what you're getting is the canonical form for this associahedron. So you take that guy, you pull it back. Now, that's if you knew about the Feynman diagrams to begin with. You've never heard of Feynman diagrams. I just tell you all this geometry. How would you find it? Well, when you have any polytope, so you have a polytope and you want to find its canonical form, right? Now, remember I told you that I told you that the canonical form of a polytope can also be thought of as the volume of the dual polytope. Okay, so just think about that in that language for a second. Let's think about what the volume of a dual might look like. Now, if you have some polytope, all of whose facets look like, for instance, imagine a 3-dimensional polytope, but all the facets are triangles. Okay, so if you have some polytope that's so-called simplicial, okay, so all of its facets just look like simplices, it is particularly easy to triangulate it, right? All you do is you plunk down any point anywhere, and then you just make a 1 higher simplex, right? You just go to each face, and that just gives you a 1 higher dimensional. That gives you a 1 higher dimensional simplex, and together they triangulate everything. Okay? So if you have simplicial polytopes, it is totally trivial to triangulate them. Okay? Now let's go back to so what does that tell us about so this is a picture of a volume, right? Let's go back to the original polytope. If the dual polytope is simplicial, what it means for the original polytope is it has the property that at each vertex, you have the minimum number of faces meeting at a point of the sort that it doesn't have to be in general. We could have more things meeting, but it has exactly it locally looks in the neighborhood of every point like a simplex around the point. Okay? And the formula we just said a moment ago translated in this language to just writing down the product of all the linear factors associated with the faces that meet at that vertex. Right? And then you sum over all vertices. Okay? So if you have a polytope such that each vertex has the dimensionalities worth of faces meeting at that point and no more, there's a simple formula for its canonical form, okay, which is just given by summing over the product of the linear factors associated with all the faces at each vertex. That's known as Feynman diagrams. Okay? Because here, every vertex is a triangulation of the polygon, which is one of the Feynman diagrams. Okay? And so Feynman diagrams correspond to one triangulation of the associahedron. Or if you like, the natural, simple triangulation of the dual associahedron that's associated, that takes advantage of the fact that it's simplicial. And anyway, there are many other triangulations. Okay? Now, remember I told you this form has this wonderful property of being projectively invariant. That means that it really has a symmetry. It has this local GL1 symmetry. Didn't have to have it. Okay? And when you write in terms of Feynman diagrams, even if we go back to the 4-point example, if I write ds over s minus dt over t, just the ds over s, that's not projectively invariant. The dt over t, that's not projectively invariant. Only the sum of all of them is projectively invariant. Okay? So that means that the Feynman diagram expansion is hiding this local GL1 invariance. It's a feature of the final answer, but we don't see it term by term. And that's actually reflected in some properties of the full amplitude that were not obvious before, but the local GL1 invariance makes it obvious. For example, local GL1 invariance tells you there's no pole at infinity. Okay? And so if you take the answer, you set on the subspace, you search for a pole at infinity, every Feynman diagram by itself has it, but the final answer does not. So this is a prediction about the amplitude, which is not obvious in terms of Feynman diagrams, but is verifiably true. Okay? No one told you anything about all the geometry. They would tell you, you go off in this direction at infinity and something vanishes faster than it should. Okay? And it's true. It's a geometry that guarantees that it's true. So as I said, even this dumb old phi cube theory has some hidden symmetries in it. This is an avatar. It's a sort of baby version of what an n equals 4 superhanging node we think of as dual conformal invariance. So there's sort of fancier symmetries. And the Yangian symmetry of n equals 4, there's fancier things in n equals 4 superhanging nodes, but already there are echoes of that in this very, very simple example. There are other features of the answer that are made manifest here. For example, there are obvious things. Oh, I should have said. Here, I just gave you a fast argument so you can get a feeling for why this thing is the isosahedron. Okay? But you can really do it right. The way to really do it right is not to say you put this to 0, then you put another one to 0, and you see you can't cross. You just ask what this boundary looks like. And you discover, just with a tiny bit of work, that if you go to this boundary, you get the direct product of this isosahedron and that isosahedron. Okay, so you really see, that's the deep geometric fact, is that you have a collection of objects such that when you go to the boundary of one, you get something that factorizes into the product of lower guys. Okay? And that fact just follows from these inequalities in a very simple way. Okay? So that's really the sort of deepest way of seeing that. So the locality and unitarity of the scattering amplitude is reflected as basically as possible in this geometry. And everything I was just telling you for the last 5 minutes tells you that you actually learn more things about the amplitude from this geometric point of view. There's beef. It's not just moving formulas around. There's actually beefier. You learn things about this silly theory, the silly seeming theory that are not manifest term by term in the Feynman diagram. There are many other things. There are many other. There's many other features of the amplitude. There are a number of other surprising things about it, but I don't have time to explain it in more detail. Let me just say one more thing. I think this is all we're going to have time to talk about. So I won't be able to tell you about either the amplification or the cosmology of polytopes. But let me say one more thing, because I think it's rather interesting. So we have this picture now, therefore, that instead of, now we think about the amplitudes as differential forms. Okay, great. And here we have this theory with just planar poles and fine, right? Or the theory with the planar poles. So now we can imagine more general things. Okay. So and imagine you have in mind some theory of gluons. Okay. And again, normal Feynman diagram language, no fancy variables or anything. We'd have polarization vectors, we'd have momenta, right? Imagine we're summing Feynman diagrams. We get some numerators that depend on linear and polarization vectors that depend on momenta, but the denominators are always these product and propagators, right? So we have the product of the sum of p's squared. Okay? So that means that if you wanted to, you could turn them into differential forms too. Okay? Now, here's a non-trivial claim. I don't have time to explain why it's true, but it's really a somewhat remarkable claim. Is that but now that you have polarization vectors around, there's a notion of gauge invariance, right? On-shell gauge invariance, that if you replace epsilon with the momentum, the on-shell gauge invariance also sometimes called the word identity, and it's very important from any point of view, is if you replace epsilon mu, the particle A, with p mu for that particle, the amplitude should vanish. Okay? That tells you that there's no longitudinal photons, if you like. Right? You're only propagating the physical modes. Okay, so here's the non-trivial plane. Oh, and if you have Yang-Mills theory, of course we could imagine we have higher dimension operators, more complicated theory, but there's the simplest theory with two derivatives that has the minimum number of momenta upstairs, right? So it has the smallest number of, it has the smallest number of momenta upstairs. So with those caveats, the claim is that there is a unique differential form on kinematic space, again, with polarization vector as prefactors, which is gauge invariant, which is on-shell gauge invariant. You don't have to say anything else, right? Oh, and it's projective. Unique, projectively invariant, exactly the way that I said. So it has it's only a function of the ratio of the s's. Okay, unique, projectively invariant differential form, which is on-shell gauge invariant. Okay. For example, remarkably, it's permutation invariant as well. I didn't say anything about being permutation, but it's unique. So it happens to be permutation invariant. Treats everybody the same. Okay. So in other words, you start building these differential forms. You throw in some extra information. You want to know about spin. You throw in polarization vectors. You want to make sure you're not propagating any extra crappy states. You have to be on-shell gauge invariant. Poof! It's just uniquely fixed. There's this unique form. Okay. Now, the claim is that this form is the Yang-Mills scattering amplitude. Level. But you can ask, what the heck am I talking about? This is just some differential form. Non-abelian Yang-Mills theory has all these color factors, all these FABCs. Right? Where are all the color factors? And the answer is kind of remarkable. The color factors are actually there. The differentials in the differential forms can be treated for color factors. So let me. This is the last thing I'll say. I think there's something important about this because you can ask, what is this differential form about? Here I told you this trick that some of you have seen in geometry, but what does it bind you? What are these differential forms about? And it seems like these differential forms in kinematic space are intimately related to color. So something that you may have followed or heard about if you even pay cursory attention to what's going on in the amplitude subject is people talk about color kinematic duality. That there is some relation between color and kinematics and so on and so forth. This is the most primitive illustration of it. It's rather striking. So here's the claim. Suppose I hand you some graph, any old graph, any labels I want on the outside. Doesn't have to be planar, but I can draw it. Of course, I can always, with some appropriate labeling, I can always make it look planar, but it doesn't matter. Okay? You take any old graph. On the one hand, with this graph, if you're a particle physicist, you would associate a bunch of color factors, right? You take F, A, B, C, F, the product of all these Fs, right? Summed over all the internal guys. So for instance, with this one, you would have F, you have F1, 2, E, F, E, 3, 4, and so on, okay? So on the one hand, with every graph, you have some, with every graph, you have some product of FABCs. With each vertex, there's some FABC, and you associate, you take the product of all those Fs. On the other hand, exactly the same graph, if you instead of caring about the vertices, you think you care about the edges, there's the wedge product of the ds's that you have associated with all of them. Okay, so there's two objects that we have associated with a given graph. So on the one hand, we have the product of all the FFFs associated with the vertices. On the other hand, we have the ds wedge, ds prime, dot, dot, associated with the edges. Okay? Now here's the quite beautiful fact. These objects satisfy algebraic identities that are the Jacobi relations, that come ultimately from the Jacobi relations. Okay? The claim is that these objects satisfy exactly the same identities. So what do all the Jacobi relations come from? All the Jacobi relations ultimately for any graph, so take any complicated graph, however it looks like on the outside, whatever is going on the outside, take any three graphs which only differ in one spot. So first, what is the elementary Jacobi relation? The elementary Jacobi relation is that this plus that equals 0. Right? That's Jacobi if we weight these with s's. Okay? Now I want to claim that the same thing is true for the forms. Okay? So let's say again, this is 1, 2, 3, 4. I want to say that ds12 plus ds23 plus ds13 is equal to 0. Okay? Well, that's not quite true, right? This is not quite true, but you remember there's a famous formula if you've taken do the elementary kinematics. If you have general particle scattering with general masses on the outside, there's a formula that s plus t plus u is the sum of the mass squares, m1 squared plus m2 squared plus m3 squared plus m4 squared. Okay, so there's that simple formula. Okay. So let's go back to this picture and imagine that I'm attaching this to some whole rest of the graph symbol. Okay? So what is m1 squared? M1 squared is just the p squared of that line, right? Okay. So here what I have is that the sum of the ds's is equal to, so because the sum of the s's is equal to the sum of the p squareds of the internal lines, the sum of the ds's is just the d of the p squared of the 4 external lines. Okay? So this is true. But now remember, to get the form, I have to wedge all the ds's together. So when I wedge all the rest of them together, all of these are going to get killed by the wedging. Okay? So therefore, if I take the wedge product of all the ds's in any graph, just that numerator factor, then any three graphs that are related by this elementary move on some little blob on the inside, the wedge products of the numerators will satisfy exactly the same color identity as Jacobi factors. Okay. So that means that these differential forms can be traded for color canonically. So you give me this Yang-Mills differential form that lives on kinematical space, that has singularities on the association, etc. It's unique. And furthermore, to get the scattering amplitude from it, I just take all the ds's, I remove the ds's, I replace them with the product of f's, and now it's the Yang-Mills amplitude. So this geometry is also somehow geometrizing color. And that seems like it might be more general and interesting idea. Okay? So I just wanted to mention that because that's I think the only clue we have in this story for what these forms are about. They somehow know about color in an interesting way. Instead of having carrying these Lie algebra things around, we're doing, again, more primitive things directly just with simple differential forms on this kinematical space, but these differential forms carry the same information that we normally ascribe to Lie algebra. All right, I think that's all. I managed to talk about one subject, but I think I did manage to talk about it in some level of concreteness, and thank you all for sticking around so long. Thank you. Appreciate it.